So any discussion on threads and fasteners, we will need to look at nuts and bolts as a combination, which is basically just a machine screw or a screw with a nut on the end of it, but it kind of designates, are you mechanically attaching, or are you machining into a mating piece the geometry of the threads so that you have a matching compression mechanical fit. This is the Marx Engineering Handbook. We'll just refer to some of the terminology. So the inch screws threads have the unified national, with a root radius and a larger root radius, the metric and the mandatory larger root radius root. So you have within that group the UN and the M. So unified national coarse, unified national fine, extra fine, and constant pitch. I believe there's still a UNS for you made your own thread, and you're going to have to machine both components. So in the metric series, the pitch is designated as the M, the major diameter, and then the pitch. So coarse and fine both come with that M designation. The tolerance classes then for a UN are one of three numbers, 1, 2, 3, and either letter A for external, letter B for internal. Tolerance decreases as class number increases, and allowances specified for the 1A and 2A. 3 is pretty much the finest class that you're going to get for tolerances. So the 1A liberal tolerance, dirty or hard use. 2A, 2B, the most common, and then the 3AB for closeness or fit, and accuracy, where pretty much zero allowance is needed. And then static loading, dynamic loading, dealing with vibration. Let's see the classes of fit then for the metric. You have the E, a large allowance, which doesn't show up too much. The smaller case G for the bolt and larger case G for the nut, or if we're threading into the material. And then a lot of our taps have the H values, or the allowance is called out by the numbers. So you can manage your geometry just going through the classes of fit and how the threads are put together. So major diameter, minor diameter, pitch, and then within the specifications, you're going to have an upper and a lower bound for the threads to engage. So a 29, we call it 30 degree, 60 degree sharp V. When we look at the sizes, 0, and this is the UN, so unified coarse fine. 0, I think, is a really large eyeglass screw. 1, 3, and 12 are not commonly used. 2, 4, 6, 8, 10, 5 really, in my opinion, should be over here. Once you get into the fractional sizes, then it moves from the machine numbers into just straight fractional and goes as large as you need. So the threads, the most common series of threads, 4, 6, 8, 12, 16, 20, 28, 32, and then getting into 40 and 48 if you really need to go into that level of threads. So when we look at the Major diameters, we can refer to the chart, number of threads per inch. Pitch diameters, really a lot of geometry that goes into creating this thread. So when we detail, we're probably going to see these as sharp V's. So we're going to include the triangles, not worry about the roots and the crest. And looking at this, it's kind of hard to decipher what's going on with all of this geometry, but if we look at this as a full helical revolve, and then the major diameter is to the outside, the minor diameter to the inside. Pitch is basically where the internal and the external, that pitch line is where they're going to meet on engagement and have the clearance. Let's see if they have another chart. So pretty much plenty of charts to refer to on this. So let's jump over to the quick what you need to know. As mentioned, this is the Mastercam drill chart. List the metric and the number drill bits, as well as the fractional drill bits and the letter drill bits. And then, of course, the metric is in whatever increments you buy the index in. So when we're looking for a thread, we would go to this chart and I would look at the odd 80. The number next to it is going to be the tap. And it doesn't really give me the major diameter, but for most cases, I need to know what size hole to drill to be able to tap that, put that tap in there safely without breaking it. So this chart assumes 75% depth of thread engagement. If we are in a harder material or the class of fit allows it, we could go up a little bit, and that's kind of a big jump for the diameter, so I don't know that I would go up to a 52. But in the larger threads, we can make some adjustments, and 65-70% thread engagement will only lose a little bit of strength, and usually we're designing for over what we really need. The factors of safety will give us a little bit of variation there. So 164 and 72, we don't really run that much. 256 and the M2 by 0.4 and the metric are quite common. Don't run 3s all that much. 440s quite a bit. I think in 20 years of machining, I've got maybe a dozen 448s, a handful of 540s. They're just not that common. M3 by 0.5s, quite a few of 632s. Because of the diameter, major diameter to root ratio, 632 is actually one of the weakest threads. So kind of, we cut 632s, but we don't like them. M3 by 3.5 by 0.6 comes up. The fractional 5/32 by 32, I haven't even seen a tap for, so it's nice to know that those exist, that they're there's information on it, but not really going to happen. M4 by 0.7 and 832 then are really close together, and cut a lot of 832s. Going back to the top, 1024s, probably 1032 is the preferred, and very few 12s. But if we cut 12s, usually I want to say they're 1228s, and then quarter 20s all of the time. And then 5/16 18, M8 by 1.25, M8 by 1. So you're starting to see, I kind of jumped over those, but as we get to the bigger sizes, you're going to start to see it go from coarse to fine to that maybe consider an extra fine in there. So don't run too many M9s. 3/8/16s quite a bit, occasionally some 3/8/24s. The M10 by 1.5, 1.25, and 1.0. So 60, doing the quick conversion, 60 thousandths. And then it goes down to Gotta do math in my head again, so probably about 48 and then down to 40. So just talking about the conversions to the pitch. And then 7/16s, 14, not so much. M11, don't think I've seen one. Occasionally. And then the M12, I believe, actually has 4 pitch sizes and comes down to the strength. Then we go half 13 and quarter 18 NPT. So tapered pipe fits. I think I jumped over then the 16th and the 8th. So there it is, 16th 27 and 1/8 27 for the tapered national pipe threads. And then the quarter 18, and then the metric sizes. We get up to the 3/8 NPT in size, and then the 1/2 inch NPT, and much above that is, you're probably not going to drive that with the machine. You're going to need to have some extra oomph on it, because it's a big thread, and because of the taper, they are sealing as much on the compression, and can even go to dry seal, where the threads lock and become tighter as you turn the fitting in. All right, so rather than carry one of the charts around, or carry around the Machinery's Handbook or the Marks Engineering Handbook, here are 3 formulas that you can jot down, memorize, work with, to have that same level of information for our threading. So again, the machine screws are 0 through 12, and its format is the number, and then the second number is the threads per inch. The pitch is 1 divided by the threads per inch. So when we're making the calculation, I need to know the major diameter is going to be the number times 13 plus 60. So the minor diameter becomes the major diameter, subtract the pitch. So a 1032, number 10 is the machine call out, and then 32 threads per inch. So 10 times 13 plus 60 equals 190. Divide by 1,000, or just drop a decimal in front of it. 190 thousandths is the major diameter. Pitch, 1 divided by 32, 0.03125. We'll just round that off to 0.031. So the minor diameter becomes 190 minus 0.031 equals 159. If we go back to the chart, we're going to see those numbers. So the important one here, the number times 13 plus 60. The fractional threads, then, we just convert the fraction to its decimal, and it's going to be in the format of fractional to threads per inch. And then pitch is still 1 divided by the number of threads per inch. Major diameter we convert. Minor diameter for the tap drill is the major diameter minus the pitch still. So quarter 20 is a easy one to remember. Quarter machine thread, 20 threads per inch. 1/4 equals 0.25. And the pitch, 1 divided by 20 is 50 thousandths. So 250 minus 0.050 equals 200. We go back and look at the drill chart. In the statistical analysis, there is no 200. There's a 199 and a 201. So commonly, all of the drill charts will use a 201. Metric, being so very complicated, has the M number as the major diameter and P as the pitch. So we take the major diameter, subtract the pitch, and we get the minor diameter. So an M6 by 1, major diameter is 6 millimeters, minor diameter is 6 minus 1 equals 5 millimeters. To do the conversion over to inch, so that we can relate, or in our machining, if we need to determine how the feeds and speeds for a threading operation, then I would use the formulas. So the one I like is there are 39.37 inches in a meter, and 1 meter equals 1,000 millimeters. So 39.37 divided by 1,000 is 0.03937 inches equals 1 millimeter. The reciprocal, 1 divided by 0.03937 is the 25.4.0005 that we commonly were taught, and the problem with that is I can't visualize 25.4 millimeters in an inch. Oh, so I guess my units I need to correct my units there. Anyway, the 0.03937 being very close to 0.04 makes it so that you can multiply by 4 and be very close to the decimal equivalent to the metric. So in the case of an M6, 6 times 4 is 24. I put a 0 on the end of it or multiply by 10. That puts me at 240. And the actual is, if we look back at our chart, is going to be about 2.36 or 0.236. And then an M5 times 4 is 20, so multiply by 10 gives me 200. The actual is 197. So I can be within 5 thousandths just by quickly using that information to understand how the translation. So at the end, these are all just numbers, and we are going to deal with them in a variety of fashions. If I go to the machinery's handbook, it should be the same or very close to what's generated here.